Okay, so let's work this this rolling object problem. And in this problem we have an object, and there are three objects we have: a hoop, a cylinder, and a sphere. And that object, whichever one we're talking about, starts at the top of a 2-meter incline and rolls to the bottom. And we want to know which one wins this race. Well, in answering that question, basically, what we're going to do is calculate which one is the fastest at the bottom. Since they start from rest, the one that's going the fastest at the bottom must be the winner. So let's go ahead and do this problem. We're going to do it for a general object here, a general rolling object that's at mass m, radius r, and has moment of inertia, therefore I. And we're going to solve the problem, and then we're going to plug in the moments of inertia of our various objects. So let's do this then. Now, conservation of energy tells us, there's no friction involved here, that initial kinetic plus initial potential energy is final kinetic plus final potential energy. Okay? Now, the initial situation, our object's at the top of the incline, it's at rest. So it has zero kinetic energy. So we can cross that term out of this expression. Now, when we get to the bottom of the incline, we're at a height of 0 now. So we now have zero potential energy in our final situation. So we can cross that out. So we're left with potential energy at the top equals kinetic energy at the bottom. Okay? Now, potential energy, initial potential energy, is mg times the height. So mg times the height of that incline, which we know is 2 meters, and we'll put that in at the very end. That's our initial potential energy of an object at a height h. And that has to be equal to the final kinetic energy. Now, since this is a rolling object, the kinetic energy includes both translational motion and rotational kinetic energy. Okay? And so what we saw in our lecture is that when you add that up, it's 1/2 mv squared for translational kinetic energy, 1/2 I omega squared for rotational kinetic energy. And the velocity of the object, translational velocity, and angular velocity are related. And when we did that, we arrived at an expression for the kinetic energy of a rolling object. It's 1/2 times mass of the object plus moment of inertia over r squared times velocity squared. Okay? So the 1/2 mv squared is translational kinetic energy. The 1/2 I over r squared v squared is our 1/2 I omega squared rotational kinetic energy. Okay? So if we multiply both sides by 2, divide both sides by mass, we get this, that 2gh equals 1 plus moment of inertia over mr squared times v squared. Okay? Just two algebra steps there. Divide both sides by the quantity in the brackets here. That gives us velocity squared equals something. And then take the square root to get velocity, because we have velocity squared. And you arrive then at an expression for velocity. That is this. The velocity is the square root of 2gh over this 1 plus moment of inertia over mr squared. Okay, so there's our solution to the problem. So let's consider our first object, our hoop. Now, the hoop, the moment of inertia of a hoop is mr squared. Okay, so we plug that all into this expression here. The velocity is square root of 2gh. So when you multiply 2 times g times h, that's 2 times 9.8 times our height, which is 2. So 2 times 9.8 times 2 gives you the number 39.2 in the numerator. Now in the denominator we have 1 plus moment of inertia divided by mr squared. Moment of inertia is mr squared. So mr squared divided by mr squared is 1. So we get 1 plus 1 here. And when you solve this, you get the number 4.43 meters per second. So there's the hoop's velocity at the bottom. Now, the cylinder, okay, the moment of inertia of the cylinder is 1/2 mr squared. Okay, so when we solve this for velocity, velocity is 2gh, and remember that is our number that we calculated up here. That's 39.2 divided by 1 plus moment of inertia over mr squared. So 1/2 mr squared divided by mr squared gives you the number 1/2 here. Okay, so you do that calculation, and we get a larger number than this guy. We get the number 5.11 meters per second. Okay? Now our final object is the sphere. The sphere has moment of inertia that's 2/5 mr squared. Okay? So when we calculate the velocity then, we get this same 39.2 up here divided by 1 plus moment of inertia over mr squared. 2/5 mr squared divided by mr squared gives you the number 2/5 here. So we solve that, we get the number 5.29 meters per second. So in this race between the sphere, cylinder, and hoop, the sphere gets to the bottom first. Okay, a sphere has more material concentrated near the center than a cylinder or a hoop. So therefore, less of the kinetic energy has to go into rotating the object. Okay, and that might be a little bit more clear when we do the last part, part B. Now part B says what would be the velocity of an object that just slides down the slope. Okay, like, you know, a sled that slides down a frictionless slope. Well, we can use our exact same result here with the moment of inertia set to 0. So an object that just slides down essentially has a moment of inertia of 0. Okay? And if that's the case, well, the velocity just becomes the square root of 2gh. Okay? This all becomes, that's 0, this becomes 1, and it's the square root of 2gh. Okay? Which is the square root of this 39.2 number. And that gives you the number 6.26 meters per second. Okay, so that object would win the race because this object, all of the potential energy of the object at the top of the incline goes into translational motion. None of that energy has to go into rotating the object. It's all purely translational kinetic energy. For objects that roll, some of the potential energy has to go into actually rotating the object. Okay, so since some of that energy has to go into rotating the object, these objects are a bit slower getting down that incline. And objects that have more stuff on the edge, like a hoop, more energy of that energy has to go into rotating the object. So those are the slowest objects.